Good morning, everyone. I'm Kazunari Sugiyama, the second author of our work, Sequential Recommendation with Collaborative Explanation via Mutual Information Maximization. This is a joint work with EU at Kyoto University and Adam Jatowt at University of Innsbruck. Unfortunately, E, E cannot visit SIGIR due to his visa issue. So, but he's online now, so he will present his work now. Okay, so Yu-san, please start your presentation if you are ready.
Yes, is my screen sharing in your side?
Yes, we can see your slides now.
Okay, that's great. So, hello everyone. Good morning. My name is Yi Yu, a PhD candidate from Kyoto University, Japan. And just as Sugiyama Sensei said, due to my visa issue, so I couldn't be there in person. And I very much appreciate Sugiyama Sensei's support, remote support. So I'll present our work on sequential recommendations with collaborative explanations. So this is in collaboration with Professor Kazunari Sugiyama from Osaka Seikei University and Adam Jatowt from the University of Innsbruck. So our research focuses on like how recommender system, especially in a session-based scenario, leverage past item contents to make recommendations while also providing explanations to explain the rationales behind these suggestions. So session-based recommendations refers to using only the sequence of items interacted within a period of time. So to predict next possible items. This setup allows for the anonymization of the user's personal information, which means we don't need to know who the user is. We just need to know the input of the sequence of the items. So a key challenge in explainable methods is to make explanation more detailed and relevant. Often, explanations highlight item relationships by relevance scores, majorly by attention scores between those items. So, but they miss deeper understanding on their semantics. For example, what is the item about? So, on the other hand, knowledge-based system they use aspect. They can provide more detailed information about the items because they use an external knowledge base. But they are limited by their complexity and domain-specific constraints, which means if you change to another domain, you have to get access to another domain-specific knowledge base. And in our work, we introduce a new framework into sequential recommendations, namely collaborative explanation, using only the user interaction with items and their contents to retrieve the most relevant explanations. So theoretically, within a sufficiently large pool of explanation sentences, we can transform the explanation task from the generation problem to a retrieval and ranking problem. We illustrate this idea with an exemplar system shown in the figure. So this figure, we can see a user purchased a sequence of electronic products, such as he bought a printer, a mouse, and a smartphone, and left the review for the smartphone that it doesn't support wired headphones, meaning that it lacks a headphone jack. So ideally, the system would predict that the user might want to buy a wireless headphone to match the iPhone. In this case, the user's intention is closely related to the reviews of the previous product. And therefore, the explanation along with, in this case, the explanation along with the suggested wireless headphones would accurately reflect the reason why the user would be interested in this item. And to capture the underlying rationale of item sequences, how the how to model the item sequences, we will use a shared sequence model for also modeling the explanation sequences. So they will consider both of these two sequences. This motivates us to customize the training samples for each subtask, meaning an item prediction and the explanation generation task. And specifically for item prediction, we use previous items and the previous associated explanations. For example, when we want to predict the next item, say V12, we will use the previous item V11 and its associated explanations E11. As for the explanation prediction task, we will include also the current item, which means if we want to predict the current the explanation for V12, we need to also include it as an input as well as previous explanations. Next, we show how to adapt the current sequence model for our task. Our framework has a sequence fusion embedding layer that represents first each item and each explanation with dense vectors. These vectors are combined using a weighted sum, like using ID and the semantic information from the start. And then self-attention mechanism throughout dot product between these sequences are employed to deduce their relationships. Finally, in the output layer, we predict the item sequence and the most relevant explanations using the contextual understanding from previous layers. And to preliminary verify our idea of making explanations sequentially, we tested our framework on Amazon movies and TV datasets using two representative sequence models, GRU4Rec and SAS-Rec. We evaluated the performance by record and NDCG scores at top 10, and we observed two key points. The first one is consistency of metrics. The trends in NDCG and the recall score for explanation performance are consistent with those for recommendation subtask. And the second is consistency of models. The better sequence models show better performance in predicting explanation sequences, which are also consistent with those for recommendation performance. And these two observations demonstrate that casting the explanation as a sequence prediction task is actually feasible, and that our framework is at least learnable, although there is always some room for improvement. Our results also indicate that generating explanations can negatively impact recommendation performance, which is illustrated by the red boxes in these two figures. The reason is we think considering the global context between the items when predicting explanations can cause feature contamination, which in turn reduces the item representations so as to reduce the recommendation performance. And therefore, it is crucial to ensure the explanations can capture global context while also emphasizing the current item to be explained. To address this issue, we propose using mutual information maximization to enhance the coupling of these two things in a dual way. Specifically, we choose explanation context item alignment and item context explanation alignment. So the first alignment says it ensures the item prediction process is tightly coupled with its associated semantics. This is achieved by maximizing the mutual information between the context vector, which is also the semantic vector, and with its item representation. While the item context explanation alignment ensures the explanation prediction process targets the specific item to be explained. So we gave the name of our framework by SCE and SCE-MIM for mutual information maximization, respectively. In training, we will treat SCE as a multitask ranking problem for the both item recommendation and the explanation prediction. While SCE-MIM with mutual information is to enhance the item and the explanation coupling, with the objective to find the optimal parameters theta that minimize the total loss. So that's the optimization process of our framework. And we use the Amazon and Yelp datasets for the two datasets for experiments. Following traditional like sequential settings, we first sort users' interaction in a chronological order, and then use a leave one out testing settings, which means the second to last item was used for tuning hyperparameters, while for testing, all items except the last one were used as input, with the last item as output. And to verify our claims, we compared our frameworks with traditional explainable methods like POP, PITF, and BPER using 4 sequence models. And also we compared our approach with other sequential methods that use separate models for item and the explanations. We analyzed the effectiveness of different framework variants, including SCE, SCE-MIM, and the variants using different mutual information lower bounds, followed by visual analysis and robustness analysis. So we can show the results here. This slide shows the first experiment result. First of all, we can see advanced sequence models generally performs better in both subtasks. For instance, if we apply our SCE framework to LRU rec and the FMLP rec, it will generally yield better results than SARS rec or GRU rec. And however, we can also observe a trade-off between these two things. Such rec sometimes excels in explanation task, while LRU rec performs better than recommendations. This is likely due to the different nature dynamics between the items and the sentences. Because assumptions about item preferences over timeline often do not apply to explanations. Compared to traditional explainable methods, our framework improves performance in both recommendation and the explanation subtasks across multiple sequence models. And predicting explanations without the context of items does not really make sense. To prove this idea, we also experimented with different sequential approaches. And these results demonstrate that separate sequence modeling without context, which is by the blue bars. So we can see the red boxes are the large performance loss by about 10%. In this slide, we showed compared with original sequence models, i.e. the basic sequential recommendation models like SARS or GRU for rec. They focused only on recommendation. So there is no explanation scores in both datasets. Our SCE framework adds the explanation utility to the system with only a slight loss in recommendation performance, and most importantly, by the mutual information constraints of our SCE-MIM framework, which is the last row of in each group. They mitigated these issues. So these results also highlight the importance of balancing the performance of these two tasks. And this figure illustrates the results of framework variants under different information lower bounds, like mine shown by the yellow bars. We found that the mine sometimes performs even better on simple sequence models like GRU on Amazon datasets, But this is not always the case because it demonstrates the instability of the mine estimator for the proposed task. We conducted a visual analysis to understand the impact of different components. When models degenerate to SCE corresponds to the upper leftmost model figure, there is some overlap between the items and their associated explanation representations, but they remain largely separate. Adding the MIV constraints can pull the item representations closer to the overlapping area. While including the MIE, on the other hand, they majorly push the explanation representation into the overlap. So finally, this results in a more overlap between explanation and items. They indicate a tighter alignment. We also conducted a robustness analysis of our approach. These results highlight the importance of tuning alpha and mu for optimal performance. The figure shows that a larger alpha is a fusion weight factor, they can lead to a better performance, with optimal performance around point line. For mu, the performance starts dropping significantly when it's larger than 5e minus 2. So which means the constraints to tie these two things cannot be so strong because they need also to focus on the global context of the items. So in summary, we propose a new explanation paradigm for sequential recommender system. So based on our theoretical analysis and the experimental results, we believe this is good as our approach has a good potential to be an efficient and easily implemented method for explainable sequential methods. And also, as it's the first work on this task, so we can see there are many natural extensions for future work, like higher quality explanations. Current explanation data sets, which are auto extracted from the reviews, they need improvement. We plan to use LLMs for creating higher quality instruction-based explanation data sets. And the second, then there can be different indexing methods. Like the way of indexing items, they can affect the performance. So it should be more crucial for explanation sentences. For example, sentences with similar semantic, they need closer indexes, and they also have in nature hierarchical structures. And the third point could be retrieval and editing approaches. We plan to enhance explanations using retrieval and then editing paradigm to allow for the post-intervention on the explanations. And the last work could be unified evaluation metric. We plan to develop a unified metric that reports at once of the both recommendation and the explanation performance. So thank you very much for your kind attention. That's my presentation.